My project, I'm trying to do a semi-supervised learning for brain tumor segmentation task specifically. So outline of the presentation is like I will introduce the task and why it is required, then approach what I'm taking right now, the dataset analysis, some preliminary results, experiments, quantitative analysis on the scores, and then the next steps what I'm thinking about. So what the task with the brain tumor segmentation is to segment out the cancerous part. The we use like the brain MRI images, which gives the detailed information on the soft organs and tissues, and there is like no side effects with the repeated exposure of the brain MRI. However, the issue happens when like because of the less data in medical image segmentation, and so my solution is like to how we can efficiently use that yeah, unlabeled data. So, firstly, this picture is kind of taken from a paper to devise what my approach is, but it's on higher level. What I'm trying to do with a semi-supervised main teacher kind of approach. So, let's say we begin with a. So yeah, we take a whole train set and we divide it into a labeled and an unlabeled set. So for the label set, we add some kind of augmentation, and we have two copy of model. One is called the student and one is called the teacher. So we pass the label data from the student model as well as like the unlabeled data. It is employed with two different kind of noises, and it passed with like a teacher model and a student model. So the idea is like we the gradients through teacher model, it does not pass through. It is kind of updated from the student model. So what happens is like we pass a less weakly augmented image from a teacher model, such that it gives us a more stronger pseudo level for the student model for unlabeled data. So uh, we apply heavy data augmentation for the data which is going to pass through student model. And there we apply two different losses. One is supervised and one is unsupervised loss. So supervised loss is calculated between the labeled set, and unsupervised loss is kind of a consistency loss between the output of the two models. So this is a high level overview of the architecture. Uh, the proposed architecture I'm using right now, it's a simple unit 3D based architecture, and a simple encoder decoder based. So now, looking into the dataset details, I am using brain tumor segmentation 2.9 dataset, which is divided into HGG and SGG, high-grade glioma and low-grade glioma dataset. It has multiple sequences, like T1 weighted, which shows better anatomical results, the T2 weighted, which shows like high signal to water, and the flare, uh, which sequence, which is like the mostly used for the semi-supervised task for the medical segmentation. So there are multiple approaches, 2D versus 3D. Like 2D works on the per slide segmentation. I mean, it's easy and fast, whereas 3D, it captures the whole volume, which is beneficial when it comes to maintaining that spatio-temporal aspect. And but it's kind of computationally expensive. So this is I did some analysis on the distribution of GG and LGG equality images, and there is still a huge imbalance. As you can see, like 250 images for around LGG and like 50 images something for LGG. These are showing some images and mask, and on the bottom corner, it's like the low quality, and the other three are the high quality, as corresponding to their mask. Now, coming to the experiments, firstly, this Bratius 2019 datasets, it has like 250 images. And right now I'm working with 10% dataset, so it's only 25 labeled images. And I'm using Unit 3D, patch size 16, and then optimizer, I'm using SGT learning rate, this a number of iterations, 30,000. And the evaluation metric, it is evaluated on three different kind of metrics, the DICE score, average surface distance, and Hausdorff distance. So this is like the first set of results with the supervised setting. So I mean, right now I'm getting 100% result like 88.3 DICE score, whereas even for 10% it is 85.3%. And the Hausdorff distance is like 2.8, whereas for 100% it is 1.4. So this shows some of the training curves. So we can see that the loss curves are going down, and as well as like the point to note is like the dice score. It should the higher the better. The Ostrov is like the lower the better. So dice score is consistently improving over the training, and the Ostrov is like decreasing over the training. Uh, on the right hand side, the tensor board visualization, it shows like what the ground truth label is, and what the like the prediction level is. So it's kind of at the end of the training. So I mean, prediction is still good. Like this is 100%. So yeah, this shows it's like kind of learning where the uh, actually to segment out the part. Now I did some kind of evaluation analysis. Like since the dataset was small, I was trying to do evaluation with the batch size and the learning rate. So it kind of did not help me much. So I'm right now going ahead with like the highest batch size I can fit in the memory of mine, and the performance difference is very minimal. Um, Then yeah, so first is like the semi-supervised mean teacher setup. So this is like the baseline architecture that I'm trying to set up. So I had like I had a 10% supervised result with 85% on the dice score, and like Hausdorff at 2.8. And with the semi-supervised 10% right now, I'm not outperforming the supervised, but it's almost like the with the similar scores right now, in the sense. So I'm still doing some ablations where this mean teacher sometime it is like sensitive to some hyperparameters. So I'm doing some analysis on that to get the results more than like the to achieve around 100% supervised results. And so I did some analysis firstly with the like there is a thing called exponential moving average analysis. So that parameter, it's one of the most sensitive parameter for the mean teacher setup, where we distill the knowledge from the student model to the teacher model, but by how much factor. So this analysis I was trying to do, and I see a clear gain, like around 2 to 3% jump on the dice score. Not much on the first stroke, but yeah, dice score improved a lot. And so next step is like I'm moving to lower percentage of data, because I was actually looking one paper where they're just using only 5 or 10 images, whereas I'm still using 25 images. So the issue is like, since the 10% result is still very close to the 100%, the gain I'm trying to uh, with my proposed approach, the gain I'm not able to see that much. So that's why I have moved to a little bit of less amount of data, where it's like only 10 labeled images. And I'm also looking into average of different seed runs, because since it's a semi-supervised approach, so the labeled data we took, sometime it is like it may not be the best sample we take, or it might be the like the could be the best sample. So we have to take average of multiple seed runs, so that uh, like the story is more clear whether the approach is helping or not. So I have one idea that I'm trying to work on, which is with the hierarchical multi-level consistency. So enforce consistency at multiple stages of unit, but so the difference is like with the I'm proposing with it with the uncertainty measure. So the thing where I'm trying to make difference is like when people do uncertainty measure, they pass the whole data like multiple times. Uh, from the model. Like, so if we look at student and teacher, then it would be like passing the data for like 4 to 6 times through the model. So instead of passing the data through multiple times and then calculating uncertainty, I'm trying to calculate the uncertainty at different stages of the like the unit decoder stages. I get the output and upsample it and try to measure the uncertainty between them and enforce the consistency at that level. So that is what I'm trying to do. And yeah, I'm looking at like one another architecture with the Swin backbone to so that it could be the approach is not it only for the unit based architecture. It could also be generalized to transformer backbone as well. Yeah.